colloquium speaker is Dr. Keith Olive. We are extremely happy to have him here, and he's actually spending this semester with us. And he's the distinguished McKnight University professor at University of Minnesota right now. And he has been directing Fine Institute for Theoretical Physics at, again, University of Minnesota for 12 years, and he just stepped down. And he has been making important contribution in a wide range of theoretical physics, including nuclear physics, particle physics, astrophysics, and cosmology. And especially, he's very famous in pushing Big Bang nuclear synthesis and the dark matter physics. And he has just gotten last year, 2018, Hans Bethe Prize. Clearly, that's a quite distinguished prize, among others. So today he's telling us about supersymmetry and dark matter from weak scale to the Planck scale. Please.
So thank you. It's really nice to be here, especially to spend some extended time here. I'll be here through mid-December. This used to be a real easy talk to give. Well, at least the first part was there. The Planck scale part wasn't always there. As I'm sure everybody knows, supersymmetry has not yet been discovered at the LHC. And so the real question is, if supersymmetry is a part of nature, where does it sit? And, well, this is failing already. Okay. So what I'll be talking about is I'm going to try, throughout the talk, there will be a unifying theme, which is actually Grand Unification. And this is actually a great place because you have so many people involved in Grand Unification here, Lawrence Hall, Hitoshi, and of course Mary Kay. And so I come at the whole problem always starting with the idea that there is some sort of underlying grand unified theory, and everything is built down from there. So the main question is low energy supersymmetry still viable? Because it's low energy supersymmetry that you're really trying to discover, and whether or not there's still room for that and having something to do with answering the question about dark matter. The answer to that is yes, but it's not the way we thought about it even 10 years ago. And then the question is, what about high-scale supersymmetry? If you start, it's not really where we thought it was. It's not really at the weak scale. It's definitely above the weak scale. How much above the weak scale is what we don't know. And so I'm going to push this to somewhat extremes, and they get somewhat uncomfortable extremes. But I think there's still some interest in that, and I hope I'll convince you of that. Of course, eventually, you can say no, Susie, that's almost heretical. But what I really mean is Planck scale supersymmetry. I would still expect that supersymmetry is somewhere in the theory, whether it's only realized, say, at the string scale or at the Planck scale, and nothing is left when you get beyond that. But I'll tell you what I mean by that. So I'm going to start with unification. And you can ask the question, first question is, why do you talk about a unified gauge theory? And, well, they're very pretty. And they're simple. Simple, of course, has a question mark there because what looks simple to you after you've looked at it for a long time may not be simple to you the first time you see it. So when we get to the end of the talk and I show you a theory, you may not think it's so simple, but it really is. They've been very useful for things like other cosmological questions like baryogenesis and inflation. So to me, they're really a part of the integral part of cosmology and particle theory. And testable also gets the question mark because we started with grand unification in the 70s and the idea that they lead to detectable proton decay. That still might be a true statement, but of course proton decay hasn't been observed yet, and whether or not that scale is right around the corner or whether that scale is another 3 or 4 orders of magnitude beyond where we are is something we don't know. Then the second underlying theme here is supersymmetry, and the question is, do we have weak scale supersymmetry? And that, of course, does get the question mark. Do we have dark matter from supersymmetry? Again, we don't know. I should put a question mark there as well. Supersymmetry, of course, certainly can give you dark matter, which is, again, one of the things that I'll be stressing throughout. And what we don't know is what is the breaking scale? Supersymmetry is not a good symmetry of nature. It has to be broken, but we don't know what that scale is. So I'm going to go through this in steps. I'm going to assume that most of you don't know what a grand unified theory is and how you build one. So I'll take it a little bit slow and pedantic, at least to start with. So if you start with the simplest gauge theory, U1 gauge theory, is 1 degree of freedom, and usually that's the vector field A mu. It would be the photon, for example, if you're doing U1 electromagnetic. And you could describe matter by a single quantum number, which if it was electromagnetic, it would be the electric charge. Once you go to the standard model, the Electroweak theory, SU2 cross U1, SU2 left cross U1 Y, which is standing for hypercharge. So I say it's not really a unified theory because we have 2 gauge couplings. So each of the gauge groups, SU2 and U1, are described by separate gauge couplings. The matter representations now can be written in terms of a fundamental doublet for SU2. And so if we're talking about the electron and the neutrino, you would write them as a doublet, a left-handed doublet. And the other half of the electron is sitting there as an SU2 singlet. And they have U1 charges now described by Y. They look a little bit random, but they're arranged in such a way that you get the right electric charge Q, which is just a combination of the weak isospin and that hypercharge. So that's still pretty simple. And you would now repeat this. You have 3 generations of these, and you would do it for the quarks as well, which I'll get to next. So continuing with SU2 cross U1, there are now 4 gauge degrees of freedom, 3 plus 1, 3 for the SU2, 1 for the U1. Usually you can write the 3 for the SU2 as Wi, and the 1 for U1 is B. These things get mixed, and so that the final eigenstates for the gauge bosons are the electrically charged W plus and minus, which is just a linear combination of W1 and W2. And then the neutral gauge bosons, which are combinations of W3 and B. One is the Z boson, the other one eventually is the photon. The theory has to be broken. We all know that the theory is broken, and now that mechanism has been verified by the discovery of the Higgs, but it's broken by adding again, an SU2 doublet to the theory, and it has a hypercharge, in this case, hypercharge of 1. There's a potential for the Higgs, which leads to symmetry breaking. So the simplest model seems to work really quite well. Writing down a model for the Higgs of just lambda, a single scalar field, lambda phi to the 4th, plus m squared phi squared. If the m squared is negative, then that leads to symmetry breaking, where the field phi, in this case it would be the neutral component, picks up a vacuum expectation value, which is of order m squared over lambda. That is presumably the weak scale, and that generates masses, for example, for the gauge bosons, MW being proportional to that Higgs VEV, and MZ also being proportional to the Higgs VEV. And the photon being the massless combination is the U1 symmetry that gets preserved out of this. And as I said, this theory works incredibly well. The strong interactions are covered by another gauge group, SU3 color. In this case, there are 8 gauge degrees of freedom. They're the gluons. Matter is now put into a fundamental representation, a triplet. So given the arbitrary colors, blue, white, and red if you want. The quarks, however, so this is, for example, the up quark, but the quarks are also arranged, the left-handed parts are arranged in SU2 doublets. The singlets, the right-handed parts are arranged in singlets, UR and DR. And then they also have their various hypercharges. So it looks like a little bit of a random assemblage, despite the fact that it really works quite well. So if you summarize the standard model, you have all 3 gauge groups. There are 12 gauge degrees of freedom. I can write the quantum numbers for them in this way. So there's an octet, the 8 gluons, which are SU2 singlets. I have the SU2 triplet for the WI, and then the B gauge boson here. And the matter representations, there's the quark, there are triplets under SU3, doublets under SU2 with hypercharge, and then the singlets, the quark singlets, which are also triplets under SU3, but singlets under SU2, the lepton doublet, electron and the neutrino, and the right-handed electron, and the Higgs doublet. So that sort of encompasses what we need in the standard model, and then, of course, multiply the matter fields by 3 for the 3 generations. So what do we need to do if we go beyond that? Well, we have the 3 gauge couplings, and if we look at how they run with energy, so if you look at the renormalization group evolution of the couplings, so this is alpha is like E squared, is like the fine structure constant E squared over 4 pi, but now it would be the GI squared over 4 pi. And in the standard model, you can compute how these things run with energy, so that's the energy scale is given down here, and they look like they start to converge. And so that can give you the idea is that maybe there's some unifying aspect to this theory. And that brings us to the first grand unified theory, which is SU5. So that's the smallest grand unified theory that you can have that would encompass the SU3 cross SU2 cross U1. Okay. The matter representations now, you would pick a 5, it's actually a 5 bar, and a 10, which look like this. Now, you can ask yourself whether this is simple or complicated. If you stare at it for a little while, it's got everything you need. There's the SU3 triplet here, there's an SU2 doublet down here, and you'll find the same triplets and doublets and singlets here inside the 10. So the 5 bar breaks down in this way, and the 10 breaks down this way. So all of your matter fields come into now just 2 single representations, the 5 bar and the 10. The gauge degrees of freedom, there are now 24 of them. So it's considerably enhanced. It contains the 12 that we had before, the 8 gluons, WI and B, but it contains an extra 12, which you can call X, X bar, Y, and Y bar. And the decomposition of that 24, again, here are the standard model gauge degrees of freedom, and then there are 2 extras. They're color triplets and weak doublets. Okay. You also need a Higgs to break SU5, and that's the simplest thing to do would be a 24. And then you need the standard model Higgs, which you would have to have inside a 5. So again, if it's the first time you've seen it, you say, well, this is not very simple. But again, after you think about it for a while, it is. So in the 70s, late 70s, there was for me at least, a very influential paper, which Mary Kay was co-author, basically looking at the phenomenology of SU5, and this is essentially when I learned and when I got excited about grand unification. So it makes some predictions. One is that it predicts sine squared theta is the weak mixing angle, which is basically the ratio related to the ratio or ratios of the electroweak couplings, and it gives you the prediction of 3/8, which at first sight you might say is bad since the experimental value is 0.23. But this is really at the gut scale, and then you have to run it down to electroweak scale, and this is actually more or less a good prediction of SU5. It also predicts that the mass of B and M tau should be the same, again, at the gut scale. So even though that's not what we see, that's what you would expect when you run things down. And as I said, it leads to baryon number violation and proton decay. So these extra gauge bosons, X, for example, which are charged and colored, can decay, but their final states of their decay have different baryon number. They can decay into E minus and D, which has baryon number a third. They can also decay into a pair of anti-U quarks, which has baryon number minus 2/3. So there's no well-defined baryon number for the X gauge boson, and therefore baryon number is violated, and you can turn that into a diagram for proton decay. So again, this is what started generating the experimental searches for grand unification, in particular for proton decay. The lifetime was about 10 to the 31 plus or minus 1 years. Now the current experimental limit is more like close to 10 to the 34 years. But this is something that is an ongoing search. Hyper-K has now just been approved, and so there will be, these limits will be pushed higher and higher. So this is part of the testability of a grand unified theory. So if I come back to this picture, what really happens is actually this. And now, depending on what your view is and what unification, this doesn't look so unified. It looks like they actually miss. This got worse because we know these couplings at low energy to much higher position than we did, say, 30 years ago. And so where you might expect them to meet at a point, they actually don't meet at a point. Okay. So it looks like this kind of unification doesn't work. Okay. So now let's turn to supersymmetry. In a supersymmetric, what is supersymmetry? First of all, supersymmetry is an extension of the Lorentz symmetry, and what it does is introduce new operators, which are unlike operators that you normally encounter in physics. If you're doing your graduate courses, you'll have mainly bosonic operaters. You don't necessarily think of them that way, but that's what they are. The Hamiltonian is a scalar operator. The momentum is a vector operator. All the operators you normally encounter are bosonic. And supersymmetry introduces a fermionic operator, and so when you act on a bosonic state, it will turn it into a fermion. If you act on a fermionic state, it will turn it into a boson. And you can arrange the fields into two distinct type of multiplets. The algebras will separate out what's called a chiromultiplet, which rotates between spin 0 scalars and spin 1/2 fermions, and will also rotate a vector particle, so spin 1 particles into a fermion of spin 1/2. And so the gauge bosons would be part of vector multiplets. The matter fields would be part of the chiromultiplets. And in principle, there's also a gravitational multiplet where there's a gravitino, which is a partner of the graviton, which is spin 2. The gravitino is spin 3/2. And I'll be coming back to the gravitino a little bit later. So why do you do supersymmetry? Other than you can, right? It's an extension, as I said, of the Lorentz group, and so it's there. One of the arguments for supersymmetry, which I won't be going into at all today, is usually touted as the gauge hierarchy problem. There are two aspects of the gauge hierarchy problem. One has to do with the fact that there's a distinction between scales in particle physics. There's if you want, either the gut scale, which is around 10 to the 15 GeV, or the Planck scale at 10 to the 19 GeV, and there's the weak scale, which we know is at 100 GeV. So you can ask, why do you have these two scales? Supersymmetry doesn't address that one. You could also ask, why are they separate? How do you maintain the separation between the two through radiative corrections? Usually that's one of the arguments for supersymmetry, which I won't say much about beyond that. Gauge coupling unification, so I already showed you that if you just extend the standard model to something like SU5, it doesn't look like gauge unification actually occurs. And as I'll go on to show you that it is much simpler in supersymmetric theory. Then there are a couple of other more subtle issues involved in the Electroweak theory, or in the standard model, and that has to do with the stability of the Electroweak vacuum. In the standard model, you might, at first glance, say that the Electroweak vacuum is in fact not stable. That is, that quartic coupling of the Higgs potential runs negative, and I'll show you what I mean by that. There's another aspect is I mentioned when I said the mass squared of the Higgs potential was negative. You might have asked, why is it negative? Why do you have symmetry breaking to the first place? And supersymmetry offers you an explanation of how that happens through a process of what's called radiative electroweak symmetry breaking. Of course, supersymmetry also provides you with a candidate for dark matter. We'll get into that, of course. Improvement to low energy phenomenology, that one now gets a question mark, and I'll tell you what and why I'm saying that. And then the underlying question is the Higgs mass is 125 GeV, which is actually consistent with predictions of supersymmetry, and I'll go through that. But yet There is no supersymmetry that's been observed. And actually, those two statements are, in fact, consistent with each other. So let's back up for a second and look at, again, the running of the gauge couplings. That's in standard SU5. But if I go to the supersymmetric version of that, the coefficients of those beta functions are a little bit different because there are new particle degrees of freedom because of supersymmetry. And what happens is that the running of that, this is assuming that supersymmetry comes in at about a TeV, so 1,000 GeV, and bends those, the running of those gauge couplings, and then they look like they unify at some high energy scale. And then if you're really sharp, you'll see that they don't quite still unify, but maybe that's okay. You could also, if you're thinking ahead, maybe they actually aren't supposed to completely unify because there are other things that are happening at the gut scale that you would have to do corrections for that. But still, this picture looks in terms of unification much better than that one. So now the stability of the Higgs vacuum, so there's the Higgs potential again. And there are two issues here. One is what happens to lambda. So you can also ask about what happens if you run that quartic coupling up to high energies, just like you were running the gauge couplings. And you would find that it actually runs negative at some high energy scale, around 10 to the 10 GeV. Okay, it's a little bit easier to see here. That, of course, would be disastrous if the coefficient of phi to the fourth were negative. That would represent an instability in the vacuum, and that would lead to the expectation that there are other, either the theory is sick if there's nothing to fix that, or that there are other minima that we should in fact be living in. So, and it's close whether this actually really goes negative or not, but it would be nice if this didn't happen, and then again coming back to the m squared. Now what happens in supersymmetry is that lambda is not just really a free parameter. Lambda is calculable, and in fact it's given at the tree level, it's given in terms of the electroweak gauge couplings. And in particular, it's the sum of the squares of those two gauge couplings, and so it's positive definite. So it can never run negative, and so you ensure the stability of the electroweak vacuum, even if you're running up to very high energy scales. So that's another benefit of going towards a supersymmetric standard model rather than the non-supersymmetric standard model. And as I say, you also get radiative electroweak symmetry breaking. What I mean by that is that m squared will actually run negative. So it's a little bit more complicated of a plot, but it's a valuable one. First of all, it already utilizes some things I haven't introduced yet, and that's the idea of some simplifications in the supersymmetric spectra. So here I have a parameter m0, which is a scalar, unified scalar mass. I'll come back to this. So I'm saying that all the scalar masses at some high energy scale, so near the Grand Unified scale, have the same value. All of these are the gaugino masses. These are the masses of the partners of the gauge bosons. I'm going to say that they all have the same masses at high energy scales. And this is the Higgs mass. I didn't mention yet, but there are actually two Higgs doublets in the supersymmetric model. And they have a mixing mass term, which is mu. That's a supersymmetric parameter. And they have a breaking scale, which is this m0. But here everything is positive. What happens in a supersymmetric model is that when you run this, one or both of the Higgs mass squareds actually runs negative. So if you just run things down, scalar masses do what they do, and you get a spectrum of particles at low energy. That's important because that's what lets you calculate anything at low energy. For example, the dark matter relic abundance at low energy. Same thing with the gauginos. If this is the lightest one, for example, you see here, that's the lightest supersymmetric particle. That's the partner of this B gauge boson. That would eventually become your dark matter candidate. So that's, again, given these numbers, you can calculate everything that goes on at low energy. It's a very simplified model, but that's it's also very predictable. And so as you run down to low energy, one of these mass squareds runs negative. This minus sign actually refers to the mass squared, and that triggers for you electroweak symmetry breaking. So another question is now able to be answered in the context of these theories. So what is the minimal supersymmetric standard model? Well, it gives you partners to all of your standard model particles. So every single particle that we know in the standard model would get a partner. So if it's part of a chiral multiplet, it starts out as a fermion, it gets a scalar partner. If it's a vector, it's in a vector multiplet and gets a fermionic partner. There has to be one extra Higgs boson, so one extra electroweak doublet. That's the minimal thing that you would have to add at low energy. What's also minimal, typically, is to add the minimal number of new interactions. So once you have all these things, in principle, what you would say is that, well, you should allow all interactions that are possible due to gauge invariance. And that would give you more than the minimum, and in particular, it would give you a whole bunch of them that lead to very rapid proton decay. And so that would almost instantaneously rule out the theory. But there's an easy way to fix that, and that's to impose a symmetry which is called R parity, and it's related to baryon number, lepton number, and spin. And if R parity is preserved, then all of the unwanted interactions are immediately disallowed, and you really do get the minimum number of new interactions. That is, the only interactions you have are supersymmetric versions of standard model interactions. So take any standard model interaction, if you write down the diagram, take two legs and switch them to their supersymmetric counterparts, and that'll be part of the theory, but nothing else will be. Okay. Of course, the other consequence of R parity is that you get a dark matter candidate, as I'll explain. Now, which supersymmetric model? The minimal model, even with R parity, has approximately 100 parameters in it beyond the standard model. And so you're forced to that. That's just by imposing supersymmetry and supersymmetry breaking, that's what you have. So you can make some headway out of that by going to what's called the constrained minimal supersymmetric model, which is motivated if supersymmetry is broken, for example, through gravity. There are other ways to motivate this as well. And you make some assumptions about these masses. So as I already mentioned, gaugino mass unification. So all of the gaugino masses, gauginos being the partners of the gauge bosons, are unified at some high energy scale. Scalar mass unification, same thing I mentioned. This corresponded to the parameter m1/2. This corresponded to m0. There's another parameter which I don't really need to get into here. It's also associated with supersymmetry breaking, but again, there are in principle a lot of these, but there are a real lot of scalar masses in principle, but they all unify. If they unify, then you have a much simpler theory, and basically you have 4 parameters, m1/2, m0, which I already mentioned, this ape term, and since you have 2 Higgs doublets, you have 2 Higgs expectation values. Usually you take the ratio of those 2 expectation values to be a parameter, which is called tangent beta, and those are your 4 continuous variables. This mu parameter has a choice of sign. Again, I won't have to get into that very much either. So, if you have R parity, then that leads you to the conclusion that you're going to have a stable dark matter candidate. And the reason is that the lightest supersymmetric particle, which would carry R charge -1, right? The lightest R charge -1 particle would be stable, just like the electron being the lightest electrically charged particle is stable, like why the proton being the lightest baryon is, at least as far as we know, is stable, but in a grand unified theory, baryon number is not conserved, so that allows for the possibility of decay. So if R parity is exact, you would have an exactly stable dark matter candidate. If R parity is just slightly broken, the dark matter candidate might be very, very long-lived. If R parity is badly broken, you don't get a dark matter candidate. So what is the dark matter candidate? Usually it's taken to be a linear combination of either the partners of the neutral gauge boson, so B, and this would be W3, the BNO and WENO, and the 2 Higgsinos. And so these things all mix, and the lightest of these is often found to be the dark matter candidate. In principle, it could be the scalar partner of the neutrino. In the minimal model, that would be excluded, mainly because it would be very easy to detect, and it would have already been detected in direct detection experiments. You could go beyond the minimal model and still argue for a neutrino to be the dark matter candidate. And then the other possibilities, if you have an axion in the theory, it might be the axino. If you have you do have a graviton, so gravitino. And I will come back to gravitinos as being potential dark matter candidates. So how do you get the relic density? In the early universe, you're assuming that you're starting out at very high temperatures, much larger than the scale of all of these particles. And all of them are in equilibrium. So chi is representing the dark matter, the lightest supersymmetric particle. And being in equilibrium means, in this case, that all of its interactions, or some of its interactions, are greater than the expansion rate of the universe, which is given by the Hubble parameter here, just represented by h. And the number density of these particles would be equal to the number density of anything else in the radiation background in the early universe, say the density of photons. And if you look at, for example, the rate of annihilations of these things, it would just be the number density times their annihilation cross-section. That number density being like photons is t cubed, and that will and the Hubble parameter is basically like t squared. So they have different temperature dependencies. And at some point, as t drops below the mass of the neutralino, or mass of whatever the dark matter particle is, annihilations start dropping the number density of these particles. And if they're in equilibrium, they'll start being, their number densities will be suppressed by a Boltzmann factor e to the minus m over t. That can't go on forever, because if this thing gets to be too small, then they drop out of equilibrium. And so the number density will eventually freeze out when gamma becomes less than h, and that's shown here sort of schematically. In equilibrium, the number density would go down exponentially. Eventually, that freezes out, and you get a fixed ratio of these dark matter particles relative to photons. And here is an example of an annihilation of BNOs into a fermion pair through the exchange of a scalar fermion. And so for any of these supersymmetric models, you know all the parameters, you know all the masses, you know all the couplings, you know all of the cross-sections. You can just compute it. So is weak-scale supersymmetry still viable? And in what sense is it viable? So as we'll see, and I won't discuss all of these in details, that today, this kind of constrained supersymmetric model, you're having to lie in the parameter space along very, very well-defined strips. Stau co-annihilation strip, I'll explain what that is in a minute, or a stop co-annihilation strip. What this is all referring to is there have to be some very special relationship between the masses of the particles at low energies. So here's a picture from quite a while ago, I don't know, maybe 20 years ago, of the supersymmetric parameter space. This is the unified gaugino mass, the unified scalar mass. This is for fixed A, which I said I wasn't going to talk about. Fixed value of tangent beta here is 10. And what you see is that there's some regions which are shaded here. This region is shaded because the lightest supersymmetric particle is the partner of the tau lepton. So it's charged. You would have charged dark matter here, and so that would be excluded. This little region is excluded from phenomenological reasons because it would contribute to rare B decays, and that would be excluded. This pink region was sort of preferred at the time, maybe still today if you want, because it would contribute to the G-2 anomaly, that is the anomalous magnetic moment of the muon, which is seen to be off from between theory and experiment. And in this region, that discrepancy is cured. Most important is this blue strip here. That's where you get the right relic density. Now, there's two things that are going in here. One is you think, why is it so thin? Well, it's thin because, this actually even still goes back to WMAP, I believe, but it's thin because the relic density of dark matter is known to relatively high precision. We know what the number is, and so it really would trace out a line. If you knew it exactly, it would just be a line. But there is some sort of thicker region here where you have more freedom in the choice of your parameters and masses. One thing to notice here that this mass scale is going up to a TeV. This one's going out to 800 GeV. And so this is the Stau co-annihilation strip. Along this upper boundary, the mass of the neutralino, the dark matter particle, and the mass of the partner of the tau are exactly degenerate along that line. And so you see along this strip, you get enhanced annihilations, which let you go out to, at the time, look like very high energies. Okay. Now, just as a side remark is that the theory also makes predictions on what the Higgs mass is. So if I just scan the parameter space, I would get something that looks like this. Typical Higgs masses would be around 150, 118, 120 GeV. And it sort of peters out. It's very hard to get masses up above 130 GeV. If I start putting cuts, like cosmology or other phenomenological cuts, I would get this blue. If I add this, if I want to solve that G-2 discrepancy, I get something like that. But the point here is that there are very few models that would go up beyond 128, 130 GeV. Of course, now you know the answer. You know the answer is 125, and so it looks like you're living out here. Okay. So over the years, we've put together sort of a way to test these models, which goes under the name Mastercode. It's a combination of theorists and experimentalists, which takes a frequentist approach to looking at these models. So for any given model, like the CMSSM, which I was describing, you go through the parameter space. Each point in the parameter space makes a prediction of something that's either been measured or has a constraint on it, and you can form a chi-squared statistic, and you can do all of your likelihood analysis and determine if there's a best fit and where you should lie. And this was in 2009 before we had LHC results, and we made a pretty definite prediction, and there's a best fit point is that white spot there. And if you look, this is at 300 GeV. M1/2 and M0 here are flipped, and about 100 GeV and M0. There's a little red contour here, which is the 68%, 95% contour. It looked like this was well within the reach of the LHC. Supersymmetry should have been discovered. It should have been discovered even before the Higgs was discovered. As far as direct detection is concerned, prediction, the best fit prediction. This is a plot of the elastic scattering cross-section for spin-independent scattering on protons, again, as a function of the neutralino mass. And again, the 68, 95% contours. When this was done, the existing limits were sitting up here. This was from CDMS and probably Xenon 10 at the time. So that's what the best limits we had at the time. Since then, we got Xenon 100 and Lux, which were cutting into this parameter space. But the point here was that the predictions were, again, well within the reach of upcoming experiments. And so there was a lot of anticipation that not only should supersymmetry be discovered at the LHC, but dark matter should be discovered in direct detection experiments. Going back to this plot, when the LHC turned on, there was an exclusion contour that you could put on this kind of a plot. So this is, again, that old plot. And then that was, I think, after just a few days or just the first couple of weeks when first results were announced. And then as time went on, that curve started moving to the left. And this was all still really within the first year or so. I think there's one more. And it's, of course, gotten way past that. So here you would say all of that Stow co-annihilation strip is now excluded. Okay? You can argue about this, but I would even ignore this because you see there's a Higgs, I didn't mention it before, there's a Higgs mass contour here of 114. It's here, it's 119. So you know, as soon as they announced that the Higgs mass was 125, you have to be way out here. Right? There's no way that you're going to be sitting in this part of the parameter space. So we jump to this picture, which is after run 1. It's not much change now with run 2. We didn't do the full analysis yet with run 2 that's being done right now. The best fit point used to be sitting here, right? 300, 100. So it was right about there. The best fit point is now here. There's always going to be a best fit point. It's just the minimum of the likelihood function. The maximum of the likelihood function, minimum of chi-squared. This is the run 1 exclusion boundary on this kind of a plot. Again, you have your 68 and 95% confidence level limits. But what you should be a little bit troubled with is that even the 68% confidence level limit allows you to go up to extremely high masses. I mean, if you go infinitely far out here, you're exactly at the standard model. And so this does not allow you to distinguish based on the current experiments from the standard model. So that's the first bit of trouble. This is eventually, LHC didn't run at 14 TeV, but at 13, and I guess they got up to about 150 inverse femtobarns, but so this is still where a future limit will lie once you get there. What about the direct detection? Okay. So now these were relatively new results from Lux, Panda X, Xenon 1 ton. They're sitting up here, so definitely below the previous limits. This is the LZ sensitivity. The best fit point is sitting there, so with some luck, LZ should be able to still find it. Again, you have 68, 95% confidence level limits. This one's a little bit encouraging, at least, because it's all above this was so-called neutrino background, which it would be very difficult to get beyond. So those are the current predictions post-run 1. So what does this kind of parameter space look like, M1 half and M0 today? So just again, to put it in perspective, the previous plot I showed you went out to 1 TeV, which is about here, and 800 GeV in M0. So it was this tiny little corner which I was showing you before. Now I'm plotting out to 15 TeV. I'm plotting up to 20 TeV. So completely different scale. And now you see where you're lying in terms of where the Higgs mass should be out here. What you don't see are the blue strips. Well, there is a blue strip down here at the very corner, which you don't see. And there is a blue strip running here, which is so thin, A, because of now the WMAP measurement, but also because of the scale that this is plotted on. By the way, this is a proton decay exclusion here. Everything underneath here would give a proton lifetime, which is too short. So how close do you have to be? How degenerate do you have to be? The mass difference between the neutralino and the stop is now in the tens of GeV, but remember the scale that we're talking about are tens of TeV. So they're very, very degenerate. This is the Higgs mass prediction and the degeneracy between the neutralino and the stop. The stop is the partner of the top, the scalar partner of the top. And there's another example again, but it's more or less, here you see the blue strip. This has a different value of A, but this is more or less the same idea. This region is excluded because you don't get electroweak symmetry breaking. But that's essentially a detail. Now, there are lots of other possibilities that you can have for this, and I won't go through them at all, but I'm just mentioning that you can go to less constrained models, you can go to more constrained models, but I'm not going to, and anytime you'd make a departure, you generally are going to be opening up parameter space. I'm only going to show this. This is a more constrained model, but I'm only going to flash this because I want you to see that the scale is now being moved up to the PeV scale. So this is 1,000 TeV, where you again get, these are the mass parameters, but you get some good dark matter candidates. In this case, it's still a 1 TeV Higgsino, a 3 TeV Reno partner of the W gauge boson. So the mass scales could be significantly higher. What happens if you push it up even higher? And so there's a theory, this was more in the spirit of good humor, especially if you look this up and find out the date that it came out on. Split supersymmetry is a theory where the scalar masses are sent to be very high, but you let the gaugino masses stay low. Supersplit is where you put all the scales very high. And that should remind you of a very successful theory, but I'll leave that to you. If you put the scales very large, and what happens if the only thing that survives from supersymmetry is the gravitino, and that stays light? If the gravitino is the lightest supersymmetric particle, it becomes your dark matter candidate. It's going to be stable. The problem with that is really our philosophy of physics, that is it detectable. Direct detection is essentially impossible. I could say difficult, and that's being generous because this thing has only gravitational interactions. But it's still a logical possibility. Now, in the standard sort of scenario, gravitinos have been discussed before as dark matter candidates. They've also been discussed often in terms of being the next to lightest particle, giving you various signatures through their decays, their long-lived decays. But the way they're produced in the early universe is that after inflation and after reheating, you have a bath, and gluons will produce a gluino and a gravitino, right? So you're producing two dark matter particles. That production cross-section, again, it's going like G Newton, it's gravitational. Depends on the masses of the gluino and the gravitino. And you can compute that rate of production. You can compute the abundance of gravitinos. The details don't matter, but you can compute what they are. But this isn't possible if all the supersymmetric particles are very, very heavy, heavier than the inflationary scale in this case, which is about 10 to the 13 GeV. So what happens in that case? In that case, you would have gluon, but now you have to produce 2 gravitinos. And that comes at a price. Now it's g newtons squared, so even weaker. Okay? But you can still calculate the abundance of gravitinos, and you can get the right relic abundance if the gravitino mass is now up to the EeV scale. So now we're talking about 10 to the 9 GeV, well, 10 to the 8th if it's a 10th, with reheating temperatures which are still quite reasonable for inflationary models, 10 to the 10 GeV. Okay? I won't go through this again because I'll come back to it in a moment when I push things to even higher scales. But gauge hierarchy problem, no, that's not going to be solved. I didn't talk about it earlier. I'm not going to talk about it now. You can still get gauge coupling unification, and you can still get stabilization of the electroweak vacuum. You can still get radiative symmetry breaking. And, of course, I just said you would get dark matter, which is the gravitino. But I'm not going to go through that. I'm going to push the scales up now even higher. And the way I'm going to do that, the way you do it here, in fact, I guess, is to consider now a larger grand unified theory, and that's SO10. SO10 will look a little bit more complicated, but I hope you'll see that it's actually much simpler. So SO10 contains SU5 cross U1, so it's a little bit larger. It has 45 gauge degrees of freedom. It's got the 24 of SU5 and 21 others. The decomposition of the 45 looks like that. Okay, it's got that 24 and a number of other things. But what's really nice is the matter content. The matter degrees of freedom fit into a fundamental 16 of SO10. And the decomposition of the 16 under SU5 is the 10 5 bar, which contains already all of your standard model degrees of freedom, plus one more, which is associated with the right-handed neutrino. So, and that you need for neutrino masses. So this contains everything you need in the standard model in a single representation. Of course, you still need 3 copies of that. Okay. So in that sense, this is, in fact, much nicer than SO10 because everything fits. All the standard model particles and all their quantum numbers are exactly what you have in that 16 of SO10. So what happens if that's all you have? If supersymmetry is broken at the Planck scale, and really what you have surviving is just a grand unified theory, and let that grand unified theory be SO10. Can you do these things? And I'll show you how you construct a model without supersymmetry and still give you a dark matter candidate. So there are a few steps. They're fairly simple. I'm going to go through it somewhat rapidly. First thing, the 0th thing that you should do is get a copy of Slansky's review. If you're a student, this is essential. Especially if you're dealing with larger grand unified theories and gauge groups, and to just know how you deal with all of these bigger representations. This is a great review. There are probably other sources as well, but you can find this online. So I would suggest that. But the first thing you need to do is you need to pick an intermediate scale gauge group. So SO10 breaks to something larger than the standard model. So you need to pick some representation. Now you see the representations start looking a little bit funky here. They're 45s, 54s, 210s. These will break SO10 down to something smaller. And you pick one of these things, and you can then analyze it. Next thing you have to do is break that intermediate scale. And in principle, what you would like to do is use 126-dimensional representation. Again, once you get used to it, these things don't scare you as much anymore. But so you pick, but the nice thing about picking, there's a few nice things about picking this 126. First of all, it'll break you down to the standard model, plus you get a discrete symmetry out of that, a Z2 symmetry. And that discrete symmetry is actually related to matter parity or B minus L. It actually looks very much like R parity, as you'll see in a moment. But what this does is it gives you the possibility of having some representations, again, with stable particles, having an exact Z2 symmetry. In this case, it's not even put in by hand. It's part of the original gauge symmetry. The other thing this 126 does is that it gives you a way of generating Majorana masses for the right-handed neutrino, large Majorana masses, and that gives you the possibility of having a seesaw mechanism for getting light neutrino masses, so neutrino masses which are weak scale VEVs squared divided by this large scale or intermediate scale mass due to the breaking of this intermediate scale. Then you have to pick a dark matter representation. So it's not sitting in the 16. You do have to add something else, because the 16 already has everything you need for the standard model, and we need still to have a dark matter candidate. So you again have some choices of what you want to pick. Maybe the simplest thing to do is pick another 16, in this case a scalar. You could pick either scalars or fermions, and the Z2 charge of these things for the scalars, if it's a 16 and a 1 or a 144, will be opposite that of the standard model. So if you pick a 16, the lightest member of the 16 will be stable. Again, it looks like supersymmetry because it looks like a scalar copy of the matter fields. You could pick a 45, a fermionic 45. That sort of looks like the gauge fermion partners of the standard model. Remember, it's 45 in SO10. So whatever you pick here, if you pick something from up here or from inside here, the lightest thing will be stable. Okay. Now, gauge coupling unification, and this is not even a new, this has been around since the beginning of SO10. You can get gauge coupling unification because of this intermediate scale. You have 3 renormalization group equations. You have 3 unknowns. You don't know what the gut scale is, you don't know what the intermediate scale is, and you don't know the value of the gut gauge coupling. And you can try and solve this system and get a unique solution. You're not guaranteed to get a unique solution. In fact, most of the models you might try, most of your choices of intermediate scale gauge groups will give you something, completely stupid. You might get the intermediate scale above the gut scale. These are just ordinary linear equations, so they don't really care about the physics. But there are a number of cases where things do come out and you actually get gauge coupling unification without introducing supersymmetry. Okay. So I don't know if I've encouraged you or discouraged you. So the question, now I'm going to try to be a little more encouraging in the last couple minutes here. Is there hope? And the thing that I hope, at least that I still believe to be true, is that guts are still a driving force for beyond the standard model of physics. I think having some sort of unification principle, some symmetry, has got to be part of what's in nature. We don't know that yet, but that's what, in my gut, is I believe that's got to be the case. It's testable. It is testable. So there are tests you can do for grand unification. Proton decay I mentioned. It hasn't been discovered, but there are new experiments coming online to test that. Neutrinoless double beta decay, another prediction of some grand unified theories. We need to see something like that. Neutron anti-neutron oscillations. Okay, there are experiments looking for that. Again, that's baryon number, the delta B equal 2 violating interactions. And if we get more information on the neutrino spectrum. So there are still ways to look at these very high energy scales. What about supersymmetry? So I mentioned earlier supersymmetry made the prediction that the Higgs mass should be less than about 130 GeV. I was cheating a little bit because I had to say something about what parameters I was scanning, how far in supersymmetry I was able to extend. This is certainly what was thought about 15, 20 years ago. Now you can go a little bit beyond that if you're really willing to push the supersymmetric scale up very, very high. But it only goes up, the Higgs mass only goes up logarithmically with the scale of supersymmetry. So that's a prediction that came true. That was a prediction that the Higgs mass should be less than 130, and it's less than 130. Problem is that it's very close to that prediction, which means that you have to really push things, and that's what pushed the supersymmetric scale up to very high energies, which you saw with those LHC curves and the value of the Higgs mass. So the models that we were talking about, like the one I showed you where the axis only went up to 1 TeV or 800 GeV in the vertical, those are out. Those have been ruled out. Right? It hasn't ruled out the complete class of these constrained models, but they're definitely being challenged, and you have to be along these strips where there are these relations among the parameters. So it's difficult. But you don't have to be in the context of this model, and so one should keep an open mind. Supersymmetry could still be discovered at low energy. So here's an example of how these conditions get relaxed. This is a squark gluino mass plane. This is after run 1. This is what you would allow from the parameter fitting in the CMSSM. This is the LHC limit. This is the future LHC limit. When you go to the PMSSM, things are much broader. There's a lot more that's possible in terms of what range of parameters can lead to discovery. Similarly, for the direct detection, a similar plot. This is, again, in the PMSSM is 11. It's referring to 11 parameters. It's still somewhat simplified. It's not 100 parameters, but there are 11 parameters. There's a lot more freedom in how you make these choices. There could be something altogether still different, and this is something that people have thought about, we're thinking about now in the context of certain models. So here's a similar plot, M1 half, M0. Here's the strip that I was talking about before would have sitting down here. This is, again, charged staus are the LSP. And if you're up in that middle of the parameter space, why is that no good? Is because typically the relic density is way too large. Omega h squared corresponds to the relic density relative to critical density. The Planck value for omega h squared is 0.12. So what you really want is 0.1, right, for this parameter. And if you take a typical parameter value here in this 10 TeV range, you're going to get values of omega h squared which are 10,000 times too large. Normally you would think that's terribly excluded. But maybe something else happened. Maybe there was some late entropy production in the universe. Maybe there was some delayed phase transition which dumped some entropy in, and that's quite possible. And then you would actually want something like 1,000 here to get to the right value. It's not as nice as the original predictions, but it's still a possibility. So there could be some R parity violation if in this Gravitino picture that I mentioned, which seemingly is completely undetectable, if R parity is very slightly violated, then you get a lifetime of a Gravitino which might be very, very long and lead you to some signals which produce monochromatic neutrinos, again, in this EeV range. So that we're going to have to be more inventive, is the point here. So these experiments are going to keep going on. Accelerator experiments, LHC, will keep running. The upgraded LHC will keep running. Direct detection experiments will keep going, at least I hope, until you get to the neutrino floor, because I think it's important to still shut off that possibility for this sort of 100 GeV, TeV type dark matter until we know that it's not there. Indirect detection experiments are in some sense more difficult to trace back to being specific models, but they will also proceed. So experimental will still get results. And we're going to have to rely on some sort of definite signature. There's got to be physics beyond the standard model. Dark matter should exist. Baryon asymmetry has to exist. There are a number of things. Neutrino masses are present. We just don't know the mechanisms. And so without some experimental signature for a beyond standard model, we're sort of in this zone of testing models, and hopefully we'll get some results soon. So I'm going to stop there. Thanks.
Questions?
Yeah. I just like to point out that you sort of getting the V2 of all parity out of this Supersymmetry thing. And whenever you do this in the you automatically get the network constant straight. So the capture gravitation wave would be another segment of what you expect.
Sure. Yeah, it's to get the stable candidate, you need the Z2, but the Z2, as I say, you're not putting in by hand, and so it comes out of it. Yeah.
And then you get that.
Then it depends on where inflation occurs.
Any other thing? You said like only gravity, everything else is heavy.
Yeah, in one of those, super heavy.
But if it's a super heavy, like the Planck scale,
Well,
the breaking scale.
Oh no, sorry, it's
intermediate.
It's I didn't say Planck's. For that, no, that would be hard to do.
Yeah.
So this is a subtlety, right? It's a good question. Normally, supersymmetry breaking scale is related to the gravitino mass. In fact, it's the gravitino mass that generates the supersymmetry breaking. So here the idea is that you have supersymmetry break. The masses of the gauginos and scalars are above the inflationary scale. So that's let's say 10 to the 14 GeV. And now, well, it's still not trivial how you get a gravitino which is lighter than that, or how.
14 squared divided by 15.
You have to do a little bit of work of how you're doing the supersymmetry breaking, and so it's a little bit more of a detailed question. But you can do it, but it's not completely trivial.
You're concentrating on supersymmetric models for dark matter. Could you comment on what you think the likelihood of non-supersymmetric dark matter?
I'm not sure how to comment on likelihood because we don't know much. Period. One thing I will say that I didn't mention is there are if you start without supersymmetry, I think there was a model called the Higgs portal model for dark matter. It's a very simple model. All you do is add a single scalar field and it's coupled to the Higgs, that to me is. In the beginning, I wasn't too enthused with it. It looked a little arbitrary, but it is extremely simple and minimal. It turns out that something like that actually falls out of these SO10 models because that singlet could be part of this scalar 16. So whether or not that's supersymmetric or not, you could find a way, or it's maybe not supersymmetric, but it's part of some grand unified theory. There are also these kind of doublet dark matter models, which might also fall out of a grand unified theory. Now, I know these days it's very popular to construct very elaborate models for dark matter at all energy scales, and obviously we don't know, but they get to be complicated very quickly, where you are imposing a new sector of the theory for dark matter. You're imposing some interactions within that sector. You're imposing some new interactions between the sectors. We have no evidence for any of this. We have evidence for dark matter, but we don't have any information about the complexity. So I prefer still to think about the most simplest cases. And if it's the Higgs portal model, which if you're not doing supersymmetry, that would be the simplest. That's also excludable, and that's actually quite constrained now by the direct detection experiments. There's also an axion. Axion might be a dark matter candidate. Of course, completely different class of particle than what I was talking about here. So, of course, there are other possibilities, but from the top down is still my bias, if you want.
But that just asking a question about this SO10.
Yeah.
You have a full multiplet, so you have a bunch of partners, which will of course decay, but I can produce it. It's just the colored, and then it's.
Oh, but they're very heavy, though, right?
Oh, you do doublet splitting?
Well, okay. So I didn't get into that. So in SU5, just for those that know a little bit, you probably know it. If you don't know it, I'm not sure you'll understand it. But the Higgs had to be in a 5-plet. That color triplet mediates proton decay, and so you want that color triplet to be very heavy. Yet the doublet has to be light because that's what the normal Higgs is. So you have to somehow devise a mechanism to split that 5-plet into a heavy triplet and a light doublet. You can do it by brute force. That's fine tuning. There's nothing to stop you from doing it. You can do things more clever by how you derive masses for these. Then you have to have more complicated Higgs multiplets where parts of the multiplet get a large mass and parts of it don't get any mass. In SO10 you would have to do the same thing. Even to get the dark matter particle, if you have the 16, the other 50, if you want like a Higgs portal dark matter candidate, the one has to be light. But you can do it. You can write down. There are multiple contributions to the masses. You can work out all the Clebsch-Gordon coefficients. You can do everything, and then you have to tune. And so that is part of it. It's the same fine tuning that you have to do in any grand unified theory. It's part of life.
Okay. something else. Let's meet again.